All right, welcome to part 3 of our lecture video series for Monday, May 1st, where we now talk about pressure. So the way this works is I'm actually going to give you a physics definition of pressure, just like I did with a physics definition of work, right? Work is some force applied over some distance. And then we're going to kind of tweak that definition, or at least consider it from a context that makes sense to us as chemists. So let's start. Pressure. So strictly speaking, pressure is a measure of some force indicated F vector, which just means the force is pointing in some direction. So force is a push or pull. Measured per unit area A that force is being exerted over. So pressure is equal to force per area. So the way that I like to kind of introduce people to the idea of pressure, even though we've probably all, worked with gases or kind of played with gases or filled our tires or something like that before, is the following. So if you could take your hand and place it flat, palm down, onto your desk and push down with some push force, you would feel some amount of pressure as a result of you being pushed up against across the surface area of your palm from the desk back up at you. Now, if you were to change the surface area, so decrease the surface area by applying that same amount of strength in your push, but instead of down on your entire palm, down on just one fingertip, you would feel that force over that area of your fingertip being exerted like much more strongly, meaning you would feel a stronger or larger pressure. So pressure is force per unit area. What does this mean for us in relation to gases? So let's think about the source of these forces in a gaseous system. So remember, when we're talking about a gas, we're assuming that gases are modeled based on the kinetic molecular theory. So our gas particles are just little tiny balls, spheres that are bouncing around, colliding with one another, and colliding with the walls of the container that they're found in. And remember, a collision exerts some force, right? If you've got a push into somebody or you're pulling away from someone, right? That's a force, a push or pull. So the force here is going to be proportional. So this alpha symbol means directly proportional to the number of collisions in our system. And if we think about the area, we're talking about the area over which these collisions are exerted. So this is the area over which our force is exerted. So we've got kind of two scales to think of here. We've got the micro scale. This is going to be the contact area from one gas particle hitting another. So when they contact one another, they've contacted one another with some amount of surface area. This is our contact area. It's kind of like if you were to, I don't know, slam your face into a window and leave behind face oils, right? You would see the print of your face on the window. Please don't do this. On the window, right? And that print would show you kind of the map of all the contact area your window had with your face. So we've got our micro scale. And then kind of the macro scale, meaning let's look at things a little bit bigger, is not just the surface contact between molecules and also between molecules in the container, right, for each little baby molecule. This is the total amount of area that our particles are in contact with. And according to kinetic molecular theory, since we are really assuming that these molecules have a negligible volume, then we can also assume that their contact area is also zero, right? If they take up no space, then when they smack into one another, there's really like no, I don't know, contact point between them. Don't know how to say that better language. Maybe someone can help me out. But on the macro scale, if we're talking about all of the area in which our particles can collide against, what we're really talking about is we're talking about the surface area of our container. So just to put this up here again, so here we would have our area, which would be the area of our container, so the surface area of these walls. And then all of our forces are going to be all the little pushes and pulls and bounces and yada yadas that are exhibited or exerted between our gaseous particles and between the particles and the walls of the container. So this is where we kind of get the idea of pressure from a chemist's point of view. Now, in the SI system, the SI unit of pressure is the Pascal, PA. However, in chem, we like to refer to pressure relative to atmospheric pressure. So in chemistry, we use the unit atmospheres, ATM, where by definition 1.00 atmospheres is equal to the pressure of the atmosphere, so atmospheric pressure, at standard temperature and at sea level. So let's relate a bunch of our pressure units that we've got. So let's start by relating 1 atmosphere. Oh my goodness, I'm so sorry. 2 pascals. So 1 atmosphere by definition is 101,325 pascals worth of pressure. And since that's a big number, we also see the kilopascal unit. So that's 101.325 kilopascals. Something else that you will see is let's see here, torr. So that's equal to 760 torr. You'll also see some old school barometric pressure readings like millimeters of mercury. So that comes from like the barometers similar to our thermometers that had a column of mercury whose height would fluctuate based on the external pressure conditions around it. We're going to get into how those work later. So we've got millimeters of mercury, and the torr and the millimeter of mercury are basically the same. So 1 torr is 1 millimeter of mercury. Let's see here. Bar is really good for very small pressures. So this is dividing our Pascal so that it's 1 point something, so 1.01325 bar worth of pressure. And as mentioned earlier, if you've ever filled your tires before, we use here in the imperial system the PSI, or pounds per square inch. Again, pounds of force per area square inch. So this is 14.6959. PSI, or pounds per square inch. So these are all of our pressure conversions. And we are going to need to use these in order to take some measured pressure and convert it into atmospheres. So atmospheres is the gold standard for what you and I are going to use as chemists in Chem 210. So atmospheres is going to be our unit of pressure. Okay, so now that we have talked about pressure, Let's look at pressure, volume, mole, and temperature relationships. So we're going to look at gas relationships coming up in the last part of today's video for Monday, May 1st.